look at the limit of sequences. Now remember, a sequence is a list of numbers, and so when we look at the limit, we're going to be looking at what happens as n gets very large. So we're going to be taking the limit as n approaches infinity of this. So we don't really care what happens to the first n terms. We just want to see what happens as n gets very large. So the formal definition is let L be a real number. All right, the limit of the sequence a sub n is L, written as the limit as n approaches infinity of the a sub n terms, is equal to L if, for every epsilon greater than 0, there exists an m, such that if you get out past m, then the values will be within this epsilon value. So if you get far enough out, the values become arbitrarily close to a given, to the limit. And it's for every epsilon greater than 0. So now we're going to use this theorem quite a bit. If L is a real number and the limit as x approaches infinity of f of x is equal to L, and I can write f of n is equal to a sub n, where a sub n is where this is my sequence for every positive integer, then the limit as n approaches infinity of a sub n is equal to L. So if I can rewrite, represent the sequence as a function, and then if I know the function's limit, then that's the same limit as the sequence. So let's look at this one. You remember we looked at the limit as x approaches infinity of 1 plus 1 over x to the x, and we found that this was e. Using that theorem, we now know the limit as n approaches infinity of a sub n, that is also going to equal e, because I was able to replace all of the n's with x's. And the limit exists, and I know it, and I can find it. Now let's look at the convergence or divergence. Remember this sequence on the list of terms, 2, 4, 2, 4, etc. This does not converge. The limit as n approaches infinity of 3 plus negative 1 to the n does not exist. And we say that this limit diverges because it never becomes arbitrarily close to any one number. It just bounces around between 2 and 4. Now let's look at this sequence right here. B sub n is n divided by 1 minus 2n. When we look at the limit as n approaches infinity of n divided by 1 minus 2n. Now, I can do a couple of things here. I'm going to do it the way the book does it. We'll do something different in class. I'm going to divide everything through by 1 over, multiply everything by 1 over n over 1 over n. So this becomes 1 over n minus 2. Now, when I take this limit, this is minus 1/2. So this sequence converges to minus 1/2. Now, sometimes we can use L'Hopital to help us out. If I look at this function right here, a sub n is n squared divided by 2n minus 1. Let me look at the limit as x approaches infinity of x squared divided by 2 to the x minus 1. All right, so it becomes infinity over infinity, so I can use L'Hopital. F of x is x squared. G of x is 2 to the x minus 1. So f prime of x is 2x. G prime of x is natural log of 2 times 2 to the x. So this limit becomes the limit as x approaches infinity of 2x divided by the natural log of 2 times 2 to the x. Again, I get infinity over infinity. So I'm going to let f of x equal 2x. I should have changed colors, but oh well. Natural log of 2 times 2 to the x. So f prime of x is equal to 2. G prime of x is equal to natural log of 2 squared 2 to the x. All right, so now I'll switch colors. So this becomes the limit as x approaches infinity of 2 divided by the natural log of 2 squared times 2 to the x, which is 0. All right, now I'm not done. So I need to write the limit as n approaches infinity of n squared divided by 2 to the n minus 1 is indeed 0.